Hello, gentle readers. Welcome to another installment in the episodes of Logos 2000, 21st Century Foundations, where the concepts involved here are as with regards to the theory for reason and rationality, logic and mathematics, physics, and then science, and then physics again, reality, theory, naturally. So that's the idea, is that there's a consideration of the canon and the dogma and the doctrine, and as with regards to the modern theories as well, the postmodern, and for scientism and logicist positivism, that there's all sort of one theory, or at least one, that there's at least one, or at the greatest that there is one, as with regards to there being the foundations, that this is reflected throughout the course of this kind of culture of the consideration and contemplation and deliberation of things, the foundations. So that said, then today is December 25, 2024, Christmas Day. And so with regards to Christianity and Jesus as the figure of the personage of man and God and one thing, and I kind of hesitate to reflect very much on that sort of dogma and that it's and the reasoning about that, because it gets involved with the supreme and the omni and these kinds of things. And so in the course of the development of the technical philosophy and extracting that from these greatest works of all time that are still collected, the Old and New Testament as being the most printed book in the world historically, the Bible, then their Genesis 1 begins with there was nothing, and then there was space and light and time. And then the book of John 1 begins with then there was nothing, and then there was the Word. It's translated as it's written in the, for example, the Greek of that the Bible was written in Greek as of logos. That's the same word, and it means in Christianity it means Jesus. And so that then gets into all the different kind of reflections on the ethics and morals. The philosophy involves ethics and morals, and those being matters of the human condition, and what is man, as above being animal and above being machine. Man is mind, as man is human, in this sense. And so as with regards to the ethical and moral, and then that being kind of related in with regards to these works to the Mosaical, after Moses and the Ten Commandments, then you have Jesus and the teachings of Jesus. So those are essentially reflections that can be related across culturally and across cultures to the Eastern traditions as of after Buddhism and the ideas of the Confucianism and the Golden Rule, that largely is such matters of reciprocity and fairness and egalitarianism in with regards to the freedom of will and the freedom of religion, that these kinds of concepts are, of course, very broadly acculturated in religions, like the various aspects of Christianity, as vis-a-vis the Mosaical and the Christian for ethics and morals, and then as with regards to the teachings and the learnings that kind of associated with that that just kind of has its own context, and then that as well in the human condition, that such periodic reminders or marks on the calendar, the days, the holy or holidays, that then that thusly for this Christmas Day, that's pretty much all I'm going to say about that. Merry Christmas, and goodwill towards men and peace on earth is the other usual idea. So that said, then let's get into some more of the ideas of the considerations of these works here with regards to the technical philosophy. In the recent episodes of Logos 2000, what's been being considered here is kind of as part of a philosophical account, bringing in infinity and continuity as primary. These concepts of infinity and continuity are super classical. The idea is that they're also primary, first, elementary, fundamental. Thusly, natural infinity and natural continuity are the ideas that these things arise and are complete. They have their completions. That in the course of analysis, for mathematical analysis, after this kind of ideals, these absolutes, that we can arrive at in our deductive accounts, the infinity and continuity. So then this is, for example, with respect to something like the potential infinity and the absolute infinity. And that for somebody like Aristotle to take, or the figure that is Aristotle to take from his teachings in his readings, his writings, these things, is that that's one of the main concepts of Aristotle, is that we have a potential infinity. It's not complete. And so some people take that kind of as reading the odd pages of Aristotle and not the even pages, the odd and even facing pages of a book usually has a left page and a right page when you open the usual book with a spine that is the most usual sort of container of information for thousands of years. That from Aristotle, then, a lot of the dialectic is built to establish inductive accounts forwardly why out of the potential infinity is yet a reductio of the boundedness and unboundedness. The Aristotle also has actual infinity. So this is something that was already reflected on in some of these talks here, but it just helps to reflect that as with regards to infinity, then naturally it's actual. Then as with regards to our object sense being mental faculties, so we can have that as part of the story of subjectivism and intersubjectivity and interobjectivity. This got to be phenomenological, according to our sense, according to our senses. Somehow these kinds of facts or true things, that it is well one of those, that we have an object sense that has a number sense, a time sense, a word sense, a sense of the continuum, and that thusly these are also considered as with regards to the canon and the dogma and the doctrine, why they're just as part of those being necessarily relevant and relevant necessarily the accounts, and as to why that's so fulfilling and proper and begins the ideas of the things and contains and is the completions of the things. So with that said, I just imagined to read a little bit more some of these books here that I have sitting around. And from a couple episodes ago was Ogden Rood's Modern Chromatics, the history of colors and the prismatic and chromatic, about the dually self-infraconsistent dual tristimulus color space. And as with regards to the transmission and the reflection of the absorption and the emission and the intromissive and extromissive of light, why that according to that sense it's so highly developed evolutionarily in all sorts of creatures that observe it, that was just a reading into the theory of light and color and why optical light is special. This is a brief extract from a book of quite a different tradition. So, in the East and West, and the Orient and the Occident, those being other words for the East and West, the traditions have many different sects and many different, in some cases, cults. And in others, matters of belief and religion, a tradition. And so what this is from a book about the soul of the ninja. And so ninja is a Japanese word, and what it means is regards to not being seen. And so the definition of ninja or ninjutsu being its study, kind of like after bujutsu or kenjutsu or with regards to Kyoto or the Kyojutsu, the art of the sword and the bow, as with regards to the martial arts, then the ninjutsu is study of subterfuge and not being seen, the art of invisibility, say. And then ninpo is kind of the practice, and as with regards to ninja, and their key phrases are after na mu. That mu means, in Japanese, it means not yes, not no, maybe both. And as with regards to that being, then in the tradition of the modern days, then it says with regards to usually the idea of the ninjas and their outfits and their particular weapons, like the shuriken, and as regards to the tanto, or the ninja sword, the blowgun, the cat's claws, and also as with regards to various explosives and these kinds of things, the ninja. So the ninja have a philosophy, and the philosophy is reflected as kind of from this book. And I just happen to have this page of it here as with regard to the other pieces of the book. So what the author does is he starts his chapter, he quotes Carlos Castaneda from Don Juan and the teachings of Don Juan. So Castaneda was mentioned here before a little bit. He's an anthropologist, and he studied the Yaqui way of knowledge, or from traditional American Southwest type of cultural relations, and those with regards to the modern Spanish and Mestizo and Mesoamerican cultures of the day. And so he quotes him, he says this: "You have no more time for retreats or for regret. You only have time to live." And so what he talks about here is the map of the four gates. So this is a particular sort of diagram that's just kind of related to their philosophy, and it's kind of as the author describes, it's a map. And what it is a spiral of the archetypal energies, and it's related to like a four elements account of the godai. And so he says these are the forces or powers in our journey to life, about ourselves. He says in the godai, these are the energies known as ka is fire, sui is water, fu is air, and chi is earth, and ku is void. So ku is when discussed or reading from Musashi in the Book of the Five Rings, is that there's a great introductory account of Zen and Zen Buddhism. There's with regards to the concepts of the inner and the no mind, or ku. That was his ku, and that which is kind of in the presence and in the being of things, and is related to the contemplation and deliberation of things, just in matters of the perspective of mind. And so the author kind of goes on to describe this, and then there's a diagram, and the diagram is a spiral. And he says, these descriptions will give us a feeling of what it's like to be in touch with these elements of the godai. And so, whereas these elements are kind of like the traditional elements, earth, air, fire, water, and space, or the void, they're not different at all, as a matter of fact. And then he's just kind of got the ideas of that in the cardinal directions, there's like the soul, the seeker, the lower, and the megas. And then kind of between those are indecision. And in the very middle, it says the mystic elder void harmony. And that's just a reflection that is with regards to ninjutsu and the philosophy of it, that this relates mostly closely to Zen Buddhism, and as with regards to that being kind of its theory and the archetypes of its theory. Richardson's electron theory of matter. So from the Cambridge Physical Series, this book was published in 1918, and there's much to be made of it with regards to the mathematical accounts. Now, this other book that I've been reading, and it's around the corner here, is as with regards to the molecular theory of matter. And what it's about is that atoms are considered to be the constituent elements of matter. And atoms are considered to be each one their own Democritus and atom here, it's sometimes called, but their chemistry's atoms. They're Avogadro's atoms, in a sense. And they're, with regards to the nuclear models of an atom and the subatomic. It's a contradiction in words, because atomic means not cuttable, and then subatomic means within that. And then with regards to the interatomic. So what this book about the molecular physics is about is that there's the bonds that connect atoms together to make molecules. So that these atomicules, cules meaning like little animals, like the idea is and the molecules for the molarity and the molality of the gram atoms and moles, but for molecules, how the atoms are connected by bonds is the idea, as with regards to their association of their bonds. And then what the book gets into is when we learn in chemistry and physics about the atomic models and about the nuclear models and then about the molecular models and the molecular modeling. And what's first arrived at is that then there's the S and P and D or bands of orbitals of electrons, and these describe, according to the electrical theory, what are the ionic potentials of the creation of the formation of bonds. And so there's basically the idea that dissociation in a solvent, like the universal highly polar solvent H2O or water, or various nonpolar solvents, or as with regards to the existence in a gaseous medium or a liquid medium or a solid medium, that atoms connect together with bonds. And then what's learned first is about is covalent bonds, and meaning it's covalent, meaning the value either side is strong bonds. So these are also called the strong bonds. And it's considered that then other kinds of bonds end up being about the hydrogen bonds and van der Waals forces, Fritz London's dispersion forces. And then as with regards to the resonance theory that arrives first in the benzene ring, and which is a ring of carbon atoms that have like single bonds or double bonds that resonate. And as with regards to that being like, well, we don't really have a structure, just trying to connect that with making a graph network and just having these point particles, these atoms, according to their radiuses or radii, these ideas of their nuclear particles having theirs, the electrons, and then the nucleons or deuterons, pairs, or atoms, their protons and neutrons, variously charged and uncharged massive particles, which are considered to comprise in nuclear theory the quantities of mass and charge present in these configurations, their structure, according to field theory, the field number formalism and the field occupation numbers. That then this book gets into that the bonds are not merely as of given fixed angles and not merely of given fixed lengths, yet as well have their vibrations, that the vibrations are related to these resonances in a way, but they affect that it's in free play, the idea that the bonds are always, for any such matters of their state and rest, their change in motion. And as with regards to then why that molecular theory of matter is something that will be being read here a little bit more. It's a guy named Slater. He's a British guy, and it's from about 1955, when the time of the 1950s was a time of great study and research and publishing in the fields of the nuclear theories, as with regards to those being kind of classic modern nuclear theory vis-a-vis after Solomon Weinberg and the quarkian theory, and the idea that it's kind of like, well, we can talk about it in terms of giga electron volts in our massive colliding particle accelerators, all in terms of electricity and charge. That gets into the unification according to Higgs theory and those large hadrons, and that the whole quarkian theory of the nuclear forces and for asymptotic freedom, which is this great superclassical concept, that in the middle of all the concentration of power and form and structure inside the atom, that it's free in the middle. The quarkian theory, that the nuclear theory of these works and the nuclear theory of the quarkian model basically nucleons or quarks, are two different theories. And so then as with regards to there being a standard model of particle physics, it has that these are not necessarily exotic particles at all with regards to mesons, leptons, hadrons, muons, their enos, their gauge, and all these kinds of things. And as with regards to the exotic is what is called of like 1970s particle physics and 1960s particle physics, that as well as to be relayed that the quarkian and as out to the Higgsian is just kind of a subfield of nuclear theory, and there are other ones, and so then this one of these other main subfields or main fields of that is with regards to it's still quantum mechanics, it's still a particle theory, and about the derivations that make for Hamiltonians and Arrhenius and Lagrangians and these kinds of things. That it is different though than quantum electrodynamics and quantum chromodynamics, which is the quarkian, and which is the virtual photons. And so that's just to be kept in mind that as with regards to theories that are not necessarily about electron physics, that we have this neutrino, muon, and hadron physics to take account of, that these are more of the muon physics. And then as with regards to those both still having their deals to figure out with regards to neutrino physics. So that's just about beta decay, muon physics, and the nuclear theories, why these aspects of the fundamental theories of the relations of matter, it's all about matter, is the idea, is that these fields are a bit more oriented towards matter than electricity. That as well, that they're just all one theory somehow. So then this other thing that was being read a lot is that after the discussion of the natural infinities and natural continua, were continuous media and continuous manifolds and continuous functions. So reading from Gonzalez-Velasco is pretty great because he gives a very thorough account of the usual, what's the usual linear curriculum and the usual course expected to be known by all students of mathematics to achieve a mathematics degree of the differential analysis. That this is a great thing to have vis-a-vis that what came before it is also kind of good to understand with regards to the integral analysis and the differences between algebraic geometry and algebraic geometry. That then was with regards to some of the other things that are necessary is with regards to like the secular equation, Arrhenius form, and a lot of these other mathematical developments. Then besides having the entire trappings of complex analysis and that being called functional analysis, with regards to convolutional settings, here's with regards, for example, to Kodaira and Zariski and Lescope's topological surgeries, getting the real analytic out of these things, of the complex analytic, that it goes to show that these sorts of courses have that. Then it's tough to figure out a good map. There's no royal road to geometry, is what somebody once told somebody who wanted to know all of geometry thousands of years ago. Yet there are ways and ways, and furthermore, it's this matters of the philosophy of mathematics, the rigor, the formal, the reasoned and the rational, and then for the superclassical, the completions and the deductive accounts, have that. It's pretty great, this kind of book, because the author helps describe the different thinkers and what goes into it, and why we have this stack of derivations particularly, and what kind of things and reasonings go into, like why at the end they might have a course and it's like all we're going to learn is these last 5 pages, and that's going to be the subfield altogether. It's formalism, it's elements, it's objects, and then and what that means and why it is so that there's this greater surrounds, and so that's the great thing about it. So we've been talking about the wave equation, and there's some ideas as like, well, harmonics have later these superharmonics and anharmonics, and the wave equation isn't necessarily only vertical displacement. There's waves in waves. There's resonances in waves. And so trying to figure that out with regards to the Chladni functions and these kinds of things, have that then for great mathematicians and physicists like Leonhard Euler, and the idea that these things come together to make our severe abstraction, our mechanical or electrical reduction of things, have that there's yet as well that these things are decomposable and to be recomposed again. And when revisiting a part of the derivation, it kind of has to be built up all along the way. And then there's many of these things as with regards to like the stack of derivations, and it's like it's arrived at that the hypergeometric can be written as polynomials, and it's like that's about the least corner of it, because if you put that in the middle instead, then it's 0, 1, and infinity. All the numbers great and small first. And so these are the kinds of things that get into the accounts that not having kind of a super classical account first means that all this stuff has to be made classically, linearly, and to be formal and to be not absurd, with regards to the definitions of absurd and the form as from the form, or as not from the form, the absurd. That then the idea is then once there are established, like, well, we do have a couple particular things like the geometric series that adds up. Or we have our 3 models of continuous domains, we got 3 models of Cantor space, we got 3 models of laws of large numbers. And so now each one of these can kind of be their own way and things in its own justification, its own theory, all one theory, that then many of these other things can be reevaluated, the framing of what they are in a wider milieu. The fuller dialectic is the idea. Laplace transform and the inversion theorem. So the inversions are cool, and then they also have is like when it falls out that the inversions are not so held, that the inversions are anti-inversions, they're like fuller, richer, and stop using those words, that they're more thorough and completely involuted, the inversions help to express that such matters of convolution and involution vis-a-vis the reciprocal and the forward and reverse, the applications of the function and the mappings and the relation that those entail, that there's then, as we were reading up to or looking through through the definition of function, arriving at these things, then the author describes some things like he reads a lot about Heaviside, and Heaviside was a guy, Heaviside, and in the 1800s, when electrical theory was coming up, he invented some what were called non-rigorous mathematical methods, and so just be some algebra, he arrived at some things that would be for calculus and treating differential operators like algebraically, which wouldn't really necessarily hold, and it's not like after Fourier's account that the whole French school or of all its universities and the fellows of all the science came up with like these suffice for accounts of something mathematical. The Heaviside, he kind of said, well, I just did some algebraic manipulation and arrived at these terms, and look, it's you should define it this way, how this behaves. And that later there's various accounts here in Gonzalez-Velasco about how Heaviside's derivations were given at least some support, and as with regards to the empirically they work pretty well and indeed are necessary. there's a story relayed that in the time of the invention of the telegraph, and it's like, who invented the telephone? I was like, well, anybody invented the telephone, but Edison got to the post office 6 hours before this Elisha Gray from Chicago or something like that, as with regards to things like Marconi and telecommunications. That at some point in time, the idea was like, well, let's make a transatlantic cable between London and Washington or Boston, say. And the first one they did is like, well, it sank. And it's like, well, how did it go? It's like, well, I guess we should have maybe have looked at Heaviside's calculations a little bit more, because the ones we used now are failed, and it's failed. So that's pretty bad, because, you know, the theory was like to so, but it just didn't add up. But then the ones they did later with these same principles, operation after Heaviside, was like, well, yeah, that's working. And then the telegraph lines are based on the telegrapher's equation and these kinds of things. That Heaviside has that kind of going on, and so the author does get in some interesting reasons why in these particular domains in the longer accounts, and then as regards to the physical models of electricity and its real behavior, that's kind of appreciated to have that in one place, and that it's going on. Mentions Morse code. So Morse is there's Samuel Morse and if I'm not mistaken about like the Morse code, which is according to telegraphy, that it's a brief code that people can learn and that they can communicate with it at a reasonable pace, given that it's only dots and dashes, and as regards to keying it or a telegrapher's key, what is it? It's like a keyboard with only one key. Tap 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 tap. That the ideas of the Morse code is also when or it used to be the way that when people would start to learn telecommunications, it's first like, well, you put two strings together, and so you have two cans, and because you hold a string at a relative tension, if you talk into the can, it will vibrate on down the string, and you can hear it on the other side in the other can, as with regards to ear horns and these kinds of things. That later, with regards to something like the walkie-talkie, that the walkie-talkie, and it might have only had like a button to do Morse code on it, as with regards to otherwise telecommunications. It helps a lot to have these kinds of principles when trying to understand the principles of operation. Because to be like, well, what is it? It's like, it's a tablet. Well, what's on it? Is like, oh, it's got CDMA, or maybe QAM is the general operating principle of some telecommunications, and otherwise it's just a mini general purpose PC with a touchscreen display and a graphical operating system and all kinds of other peripherals, kind of all shrunk into a form factor. And it's like, well, that's great. So each one of these little parts is its own kind of thing. It's like, well, by now they glued them all together, and it's just kind of considered like, an ear horn or a can to talk into. But at the same time, it can be deconstructed, and we can rebuild it. We can rebuild him. The constant. Distortionless circuit. So the idea of out of Heaviside was how to make it so that what would arrive according to the phase and the velocity of the signals over the telegrapher's equation, that it made it possible to have at least a unidirectional communication, as with regards to the duplex in communication, two-way communication. That this distortionless was Heaviside's great prediction that came true. Because with regards to roots, and so it's interesting to see that with regards to the phase diagrams, and early in this book he has a couple different things with regards to what seem unrelated parts of mathematics, but then how in the point in infinity would like make a right angle, that nowhere on the way out do they, but yet it does. And then this other thing is with respect to propagation and phase and roots, because these are the only things we can compute with, are trigonometric functions and powers and roots, and then particular constants to their powers and roots and their inverses and forward and back. The elementary functions and number theory and stuff, that then as with regards to E and pi and phi, which is showing up a lot more in these places, it has that. Those are three great constants at least. So, and he's talking about residues, the numerical method, and with regards to the Laplace transform of circular arcs with center at the origin, straight line segments, or even parabolic arcs. About residues and circular arcs. And the paths and inequalities which help to establish relations that then in the infinitary can be seen to fulfill the relations. The inner integrals, as with regards to the order of integration, when sometimes you can say like, well, if we're doing it from X, Y, Z, then you can do it in any order if it adds up, or not. Generally the idea is like, well, no, because then an arbitrary path could be still contrived and would not add up. It's like, well, how's it done then? It's like, well, they only take derivatives instead and only take partial derivatives and then hope it's linear. And that's so. And then, well, what about when you take the integral and like these contour integrals in Gauss or Ostrogradski or Gauss-Bonnet? Well, then that's kind of a thing as after Camille Jordan, and that's also kind of from a particular perspective, say. And then as well, what is regards to this order of integration, it's like, well, you got an integral and an integral and an integral, and of course you can kind of like, for a given function for its differentials, then it's usually just kind of figured out how to arrive at it, write that as like dv for d volume instead of dx, dy, dz. And then as with regards to what those things mean and how they come about, go around. This solution in terms of trigonometric functions resembles Bernoulli's solution for the vibrating string, while the solution of the same problem found in example 8.16 by Heaviside's wave series method is similar to D'Alembert's, which are different. As in the case of the vibrating string, the trigonometric solution cannot be verified by term-by-term differentiation. But now there's a significant difference. While D'Alembert's solution was criticized as uninformative from a physical point of view, exactly the opposite is true now. To show the transmission of the pulse along the line in this case, the solution obtained by the wave series method is far superior to the trigonometric solution. In this sense, according to this development, there are others. It's around. This helps establish at least one way later to say, well, shall we sink an arbitrarily large amount of money into a transatlantic submarine cable? You know, it's according to these kinds of decisions. What are the decisions? And then he writes up about Heaviside some more and about his later accolades. And then he gets into some greater ideas about the electrostatic. So we learned some more of this from Richardson's book, where it's developed kind of thoroughly at the time of 1918 vis-a-vis this time of 1845. And about Thomson writing about Green's function. George Green, the son of a prosperous miller and baker from Sneinton near Nottingham, who had taught himself continental mathematics. That Thomson had read about the essay of Green in a memoir on definite integrals by Robert Murphy, a contemporary of Green and a fellow at Caius, I believe this at Cambridge somewhere, or Oxford, but was unable to find a copy. And then he went around and he found William Hopkins, who gave him some copies. And then Thomson read this, and then they were able to take this to be where it's used in all kinds of things. And then there's some more about Thomson and his work in electrical, the double Fourier series. And this is talking, like here it's talking about the stop derivative, like how do you get over the stop between the positive side and the negative side of the double power series. So the idea is that then this is examples in this double Fourier series about how things come together. We must keep in mind, in order to give a useful convergence theorem, that functions found in application frequently have discontinuities, but they seldom have wild kinds of discontinuities. And so here the author seems to describe that when we talk about the behavior of functions, and then these wild discontinuities are variously as with respect to whether that's the highly nonlinear or the extremes in dynamics and these kinds of things, vis-a-vis like the reading from Sedov or whatever, and he is like, we have a continuum theory, and wherever there's a discontinuity like shear, then whenever there's shear, then we have to figure it and how to model it as its own thing, and it's about the hypergeometric pretty much is what it's about. About the definitions of the continuous and the differentiable as what arrives at Lebesgue measure and these kinds of things. Bessel's inequality is with regards to the triangle rule or Cauchy-Schwarz, which is used everywhere to keep things with regards to matters of metrics and norms, that the laws are the same everywhere, or that the measures are the same everywhere. He talks about Parseval's identity again, and I've been quite interested about Parseval's identity in Plancherel as with regards to phi, the pi ratio space, and laws of large numbers and doubling and halving spaces, and the pi ratio spaces, pi rationing, that these are the formalisms that arrive at the solutions that make for the 3D, how to arrive at these things. Duhamel's principle for the heat equation. About an equation of heat propagation that includes a time-dependent term of internal heat generation. And so this is kind of like the cascade or criticality or dynamics for its own sake, kinematics for its own sake, the static and dynamic and friction. Solution is based on the following result. It was Jean-Marie Constant Duhamel, then a repetiteur, a reader at the École Polytechnique, who presented it to the Académie des Sciences in 1830 and published it in 1833. For convenience, we stated for n equals 3, but it should be clear that both the statement and its proof are valid for arbitrary dimension. By R cubed, he means an open connected set with no holes or gaps or leaps or jumps, discontinuities, and for each function and each fixed value, define another function of that as parameters by them together, and then set up a boundary value problem where the last condition is present only if D has a boundary delta D, partial delta D. Then the boundary value problem has a solution of integrating that from 0 to t dt from this other one, where it's just the only difference is left in the last term that was so introduced. So it's just basically making a partial account and taking for constants what's fixed and then having what's left, and it's like, this is the form of the equation. Then as with regards to finding the terms of that, then it's just kind of put back in the various components that make the Laplacian. So it's written here as just kind of having written the Laplacian operator here. You could also call this the Lorentzian with regards to the internal heat generation, that with regards to the Lorentzian, that Duhamel's equation or Duhamel's principle for the heat equation is relevant to the Lorentzian. And so it always just kind of assumes some action and activity that moves along, in a sense. Duhamel's principle. Poisson carried out a certain amount of work on the propagation of waves. This led him to rediscover the Fourier transform and the Poisson integral formula for the half plane. This course of this work is pretty good. And about 20 years after this book was written, then the same author wrote a history of mathematics, and I started to look at it a little bit, but then I already kind of have a history of mathematics. Yet these kinds of developments are very useful and help explain where the principles and concepts come from. And I have a number of books about differential analysis and ODEs and PDEs and like books from like the very latest, greatest, this is our coursework today in quantum mechanics and particle physics to older ones, and that this book is pretty good to kind of put together the account of where the derivations come from, and also to give the derivations, examples of them. Then here we get started mentioning about the speed of light, the fact that waves in three-dimensional space propagate exactly with speed c is known in physics as Huygens principle. So that's with regards to waves in space, and Huygens would said it would be about light in space. But then also it's picked up here is with regards to the electrostatic and electromagnetic, about the electrodynamics, the various other notions of what defines a constant named c, that is this propagation speed in space, is with regards to like the telegrapher's equation and Duhamel's principle was just mentioned. That being called Huygens, that then the L principle is that light speed is a constant in space. As with regards to that would have been kind of Huygens' original principle, and also Huygens' principle that, well, waves radiate, and then when they radiate, they also make waves. Huygens' principle, that it's among other principles of Huygens from about 1629 to 1695, who is given as the originator of the wave theory of light, and then as with regards to Fresnel. Basically, it means that in three-dimensional space, we hear sharp sounds and see sharp pictures. Now, as with regards to that, there's the soliton and instanton, as with regards to being a wave packet and all arriving at once. As with regards to like phonons and even photons, is they arrive over an extended duration of time. It's a non-zero duration of time. So when the author here, he reflects on then when we hear sharp sounds and see sharp images, and that the information and all that is kind of like so, and it's with regards to the particle model and the instantons and the solitons and the phonons and the photons, that it's as well always that's windowed and boxed. And so there's as well the surrounds of that. So all these things that have to do with diffraction in waves, and phase in waves also get involved. That is not so. But it says in the theory, it kind of makes the treatment for that is as if it were so, and it's very successful in a good theory. However, such daily experience would never take place in a two-dimensional universe. Our own senses can confirm this statement at once. A pebble dropped in a pond generates two-dimensional circular waves that move away from the point of the original disturbance. These waves reach any other point at a certain specific instant, but they do not disappear after that moment. Rather, they linger theoretically forever in the absence of friction, in a wake of ripples that do not go away. The same would be true of sound or light, and this can be demonstrated mathematically in a rather simple manner. Use the solution found above, but assume that the functions u, f, and g are independent of z. This is called the method of descent, and the details are provided in exercise 5.9. An examination of the solution so obtained shows that the domain of dependence of a point RT is a whole disk. Sounds or light emanating from all points of this disk would arrive at the point R at the same time. The conclusion is that a two-dimensional universe would be a universe of blurred sounds and sights. Life in flatland would lose its edge. And this is a great quote, and I meant to read it before. Although our derivation of Poisson's formula using spherical coordinates is three-dimensional, it can be shown using more advanced methods that the same solution is valid in Rn if n greater than 3 is odd. Thus, Huygens' principle holds in any odd-dimensional universe of dimension 3 or higher, but the method of descent would show that it is not valid in even-dimensional universes or in a one-dimensional universe. We are privileged to live in the lowest dimensional universe in which sharp sounds and sights are possible. And so this is the other day when I mentioned something about like why three space dimensions, and that this passage here kind of reflects on that. Well, at least in this mathematical model, after this Poisson formula for then as given the method of descent, that it's another reasoning as to why it is so. And there's also the existence of the cross product in 3 and 7 dimensions only. So I'm glad that's kind of what I've as far as I've read in this book yet, and there's still a couple hundred pages to go or so. So maybe we'll get to those a little bit more some later. And he talks about, now he's introduced this Ostrogradsky Gauss in this treatment. So there's the development of kind of the appellation of these things. But what I'd be really interested in kind of relate Duhamel's setup to Lorentz's setup and figured they're pretty much the same, because the whole theory was based upon Fourier and Fourier's theories of chaleur and heat as with regards to the fluid models of charge and heat and liquids. As with these things. Here's vibrations of a circular membrane. So Euler submitted a paper that the displacements of a membrane vibrating without friction, or a drum head, say, are like u sub tt equals c squared of u sub xx plus u sub yy. So this is like for the Chladni function, Chladni, that who investigated these already. This is a simplification when, say, it's not immovable or unstoppable. That yet in the superclassical is like, well, you start the superclassical with like reflections on duals, complementary duals, that neither can inductively arrive at itself in the middle, but deductively cross these analytical bridges and make these meetings in the middle of nowhere. So Euler has come up with another one of his great linearizations, a brief account of making something classical that would otherwise not be. And so then as regards to coming up with these as that being about then the system of harmonic functions and the Laplacians again, which shows up for these second partials, and their sums of the second partials in each of the dimensions. That's what it is. And that's all it is. He comes up with like negative lambda as regards to kind of like the other side of this. So this is kind of this involutive about theta double prime over theta equals negative mu, another constant. And then using the boundary conditions to make that as for constant about the general solution and the requirements must be either constant or a periodic function as to why then these sorts of developments. Then get into Bessel. Bessel is mentioned a lot, and Bessel shows up a lot. It's just got some formulas. So I'll be looking at the forms of Bessel functions, and I mostly relate these to phi. Bessel is really a lot related to phi. And so the generations of things that make Bessel should be related to phi, is my opinion. Euler revived a method already tried by Newton and Leibniz for some elementary equations, namely to seek a solution in the form of an infinite series. And Euler with his infinite series and his telescopic and stuff like that, sometimes it's great and sometimes it's like it's vanishing. The gamma function, and then this gets into the gamma function or factorial for non-integer inputs, and there are a variety of definitions of the gamma function and a variety of approximations of the gamma function of the factorial. I even found one that somebody I'd never found before. After the three Cantor spaces, but three models of Cantor space. As part of it, factorial exponential identity, which is not so in the finite, especially is it like is it super classical? It's like I guess so. And it's like well, what's its classical form? It's like doesn't exist in the classical. It's merely solely superclassical. That then this equation in the limit, or rather in the infinite, for relating the factorial and the exponential, then arrived at in the middle of that like an expression for the factorial as the square root of the sum of n to the n minus sum of n to the n. That it took me a while to convince reasoners, with regards to the convergence theorem, that much like Stirling's formula for the factorial, although it does not appear to converge, it does. And so that's one of these kinds of things that, as far as I know, I discovered that, and it's part of mathematics. This function, he's talking about Fourier, and here's Bessel, Friedrich Wilhelm Bessel, out of his Königsberg Observatory. While investigating the cooling of a cylinder, some orthogonality properties in integral form, it's used in the terms of certain generalized Fourier series, and even in this graph. This function was also an essential component, but now for any integral value of p, of the extensive studies on the motion of the planets carried out by the German astronomer Friedrich Wilhelm Bessel, of the function I sub k to the I for different values of I. The function I sub k to the, so it wouldn't be necessarily the imaginary here, I imagine. This function was named after Bessel by Jacobi in 1836, and also by Schlomilch and Lipschitz. In 1868, Heine proposed to name it Fourier-Bessel function to give credit to both researchers, but this term did not catch on. So now I'm looking at this with regards to the factorial and its placement of gamma function in the Bessel functions, and then I'll be looking at with regards to that. There phi goes in there is basically what that's going to be about. Phi does not have many very well explored or many well known, but there are many well-known properties of phi with regards to other elementary functions, and with regards to these sorts of well-known polynomials and special functions, as with regards to mathematical constants. Recursion formulas for Bessel formulas, infinite series recursion formulas, more kinds of Bessel functions, the zeros of the Bessel functions. The Bessel functions have quite a broad number of parameters, and so they show up all these different ways, and then it works out they have certain invariants that then they can be treated algebraically as to how they come and go from all these different forms. Whatever fits can fit, and whatever fits does fit. And he talks about the roots of the forms or where they cross other forms. Meaning, like, the roots sometimes are like, well, just draw the function on the xy plane, and wherever it crosses x or y, it's a particular, it's the abscissa or the ordinate of this function that also happens to be a zero. And so, related to the theorem of the theory of polynomials, or the fundamental theorem of algebra, that's what it's called, is that polynomials have roots, and those are solutions, and it has a given a number of roots according to its order, and then they may have a certain multiplicity, and they may or may not be real, but if they're not, then they have complex roots. And so the fundamental theorem of algebra then reflected these zeros, and as regards same thing with like the Riemann function, Riemann hypothesis, as with regards to factorial. In part, have that this is related to then means and methods of the fundamental theorem of algebra for roots and polynomials and their zeros. Otherwise, with regards to the diagrammatic in the setting where it's like, well, these functions make for like this an analyticity, either integral or differential, as about where these things cross. And then that's often taken up into the complex numbers, because at least there's some places where those cross, and there's a diagram for them. Then here, there's this whole identity dimension back from the differential dynamics, descriptive differential dynamics, which makes for a really great account of like, well, you just have x equals y and call that the identity dimension, and now draw stuff within on that, and then also in terms of two quadrants made by those two octants. And so for the whole thing then, and you can have complex left and complex right on either side of that. Two different things with two different definitions of a plus bi or ai plus b. That this makes for this sort of original analysis, because that's what it is. The identity dimension is just a long origin with regards to all these linear fractional equations in the integral. That somehow all that works together is the idea. But here there's a long amount, and a lot goes into helping explain the great facility of Bessel functions. Fourier-Bessel series, Dini-Bessel series, Dini, Dini-Bessel. That all these things are just fantastic. See, for instance, K. Yoshida, Lectures on Differential and Integral Equations, Interscience, 1960. See, for instance, G.N. Watson, Cambridge University Press, 1958. Dini-Bessel. And so now he gets back, after all that consideration of the Bessel functions, to the vibrating membrane, or the drum head. Usually a circular or sometimes a square. The idea being that the wave equation is propagating on this as according to how it's considered, whether it is in a state of motion and coherent motion with the constructive and deconstructive interference of waves, that the constructive and deconstructive interferences waves is adding them up, and so it's really a key thing to help find all the zeros of them. And then just with regards to what impulse, like after the Chladni functions, makes various organizations of these things. Then there's that the attenuation and dissipation is that Well, it's constantly dissipating and attenuating somehow. Then either whether that's just enters a resonant floor or a flat floor, or the Euclid and Poincaré smooth and rough planes. For that attenuation and dissipation of the oscillation and restitution. These things. The periodic Sturm-Liouville problem is consulted. And then as with regards to the Fourier-Bessel series, what this means is that the sound of a drum is not as good in tone quality as the sound of a string instrument, or the theory is lacking. On the other hand, there is something in common between the individual vibrations of a drum and those of a string. In the same manner as there were nodes in each of the component vibrations of a string, there are nodal lines in the vibrations of a drum. That is, lines that do not move at all with the passing of time. The amplitude, or things move through them, they hold as much as they don't move in the passing of time. The amplitudes of the individual vibrations for the drum of our problem are constant multiples of these functions given. And he says, see Weinberger, 1965, Abramowitz and Stegen, the great handbook of mathematical functions, one of the greatest books of just a table of functions ever, from the National Institute of Science and Technology, 1965. That then he gets into a breakout of all these different accounts of ways to look at these different regions and then help give them qualitative aspects with regards to shape and scale parameters, they're called, in distribution. It's like, well, what is that? It's like, well, we got a one mathematical function that defines this distribution. It's like, well, how does it have these 20 different things? It's like, well, in ways. It's like, well, according to these scale parameters is how big it is. And according to these shape parameters is its more qualitative aspects, or how it makes surfaces and forms, these kinds of things. As with regards to what's noted as figure 10.3 as being about given ways to assign positive or negative signs to various areas and how those will hold. With regards to various applications of the drum, and also the entire unlinear impulse that goes into it. We get into more modified Bessel functions, all kinds of Bessel functions, parameterized, implicits, and all these kinds of things. Well, that's what I hope to get to today. Was that the other day I had hoped to read that quote about 3D space from Gonzalez-Velasco. And so that's a great course to kind of complement otherwise having already a mathematics degree and sat the courses for differential analysis. And then reading this book about, and these other ones about Tinkam's group theory, Slater's theory about chemistry, and Richardson here about electrical theory, and then also as regards to Sachs and nuclear theory, that's another book I'm reading. And so Sachs and Slater kind of have a similar kind of course, S-A-C-H, Sachs, and S-L-A-T-E-R, Slater. And then that's kind of what I'll be getting into some more as time carries forward. So I wish you all have a great day. Merry Christmas. Merry Christmas. And peace on earth and goodwill towards men, and peace be with you and also with you, and these kinds of things. And warm regards.